Okay, it should start a record. Okay, and now let's share the screen and continue our work. If you can help me, can you check a little bit to see if the meeting is recorded? Because I want to be sure that
It's
everything.
recorded.
Thank you. Yeah, there are students that I understood that you have classes in this interval of time, and if this happens, for those who have classes, it's impossible to join, unfortunately. So at least they will have the opportunity to follow the recording. All right. By the way, I don't know how it appears to you, but can you see the OneNote page? I shared my screen, but I'm not on. Let's try one more time to share. All right, just a second. Okay, now I think everybody has the screen of OneNote with our with the exercise we solved last week. Do you have it in front of your eyes?
Yes.
Okay, good. So last time we started an exercise to determine the domain of convergence and to compute the sum of some series. All right, I solved it with exercise A and I left exercise B as homework. Did anybody solve it? Exercise B? If not, it's okay, because I want to do it with you to be sure that you know how to do it. All right. And as I said today, I want to continue with power series. You will have a subject from this chapter, so you'll have a power series to determine the domain of convergence and to compute the sum of a series. I want to be sure that everybody knows to that, so we'll work more, and then in the second part of our meeting, expansions in power series and some approximations. All right, so let's continue with exercise B. At B, we have to determine the domain of convergence and then to get the sum of the series. So to work, let's start the work. All right. Just a second, because I want to. All right. So the same thing we did last time for exercise A, we do now for exercise B. I have series, and n starts from 1. It was just a little bit because I don't have the exercise in front of my eyes. So I found it. That's here a series of general term minus 1 power n times x power n plus 1, everything over n. Okay. Now, let's determine first domain of convergence. Remember how we do that? Well, we take the radius, we compute the radius of convergence. Remember that for the radius of convergence, there were two formulas to use for the computation of R. Sometimes one of the formula is more useful, sometimes the other one. Okay, which one do you think it will be suitable in our situation?
The ratio formula.
Good, very well. Yeah. So let's do it. I'll have limit when n goes to infinity from minus 1 power n over n times the reverse of an plus 1. It will be n plus 1 over minus 1 power n plus 1. Okay. But because I have the module -1 power n or power n plus 1, it's 1. So we get only n plus 1 over n. I write without the module because n plus 1 over n, it's a positive. It's a positive value. All right, here, obviously the limit is 1. I hope that's clear for everybody. So if we remember from what you learned at the course, the series, it's convergent for x in the interval. So it's convergent for x in the interval -1, 1, open both sides, of course, and the divergent when x it's in -infinity, -1, reunion by 1 plus infinity. Okay, now I have to check what happens on the extremities, I mean on r, on 1 and -1. So I take 4 here. It's written. So for x equals, when x equals to 1, I get the series of general term -1 power n over n times 1. I won't write it anymore. And now who can help me to tell me how it's this series we got here? Divergent or convergent?
Is convergent according to the Leibniz test?
Very well. It's convergent according to the Leibniz test. Yeah, I will put between the parentheses the Leibniz test. Okay. Let's move forward. And I will take now x -1. Let's see what we get here. Here what we have, it will be -1 power n over n. Now it will be -1 power n plus 1. Okay, that's -1 using some elementary operations with powers. That's 2n plus 1 here at the power. Everything over n. Okay. But -1 power to n plus 1, how much will be always?
-1.
Exactly. -1 is a constant. I put it in front. So actually, my series is minus the harmonic series, which we all know that's how.
Divergent.
Good. So if we look a little bit at what we got, I see that for our case, the domain of convergence, I will put like D, but be careful, it doesn't mean it's divergent, yeah? I write like this D, and I mean the domain of convergence. It will be the interval -1, 1, but opened to the left and closed to the right, isn't it? The domain of convergence. All right. At least till now, is it clear? We didn't finish. We finished the first half of the exercise, the one which asks us the domain of convergence. So everybody understood what we did till now? Questions? Okay. Now, it comes the second part, the one when I determine the sum of the series. Well, what I do, as we did at the seminar, I will denote by something the sum of the series, because what I have here, let's lift a little bit the page to be more visible. So I have the series of general term minus 1 power n times x power n plus 1 over n. That's a series of functions. It's a power series, but in particular, it's a series of functions. So its sum, surely it must be a function too. So I will denote that function by something. I will denote it by s. Yeah, it's so denote by s of x. The sum of the series, so sum from 1 to infinity, from minus 1 over minus 1 power n over n times x power n plus 1. Okay. And if you remember from the seminar, in these situations, I told you or to integrate term by term or to derive term by term. But at this exercise, what do you advise me to do now? Something said, someone said something, unfortunately, I didn't hear. Sorry.
No, nothing. Someone gave me my room.
Okay. Look at something. If I try to derive term by term or to integrate term by term for this series, it will be something more complicated than the first series. So that's not a good idea. Okay, but what to do? Because I have to do something. But look at something else. At this series, it's better if you look. So I will denote. Just a second, if you look, if I will multiply by 1 over x, maybe it's good to explain you like this, because I'm sure that it will be more clear. So when I divide by x, all this equality, it will be s over x equals to sum from 1 to infinity from minus 1 power n over n times x, at which power will be in this case? I divided by x, don't forget. N. Exactly. Now, for the series, you just look at the series I got. What do you think I can do now for this one? Derive it or integrate it term by term?
We can derive it.
Exactly.
Derive it.
Exactly. So now a good idea is to derive, but I can't derive. If I will derive this equality, I don't think it will be something nice. I will get a differential equation, and for the moment you don't know how to solve a differential equation. Probably you will study that in the second year. So I will avoid to meet with differential equation. So that's why I will denote this series by something, I don't know, maybe f of x. So I denote by f of x the function. The sum of the series, it's also a function, but I wanted to say that I denote the sum of the new series with f of x. Now I will derive this one term by term. So I get f prime of x equals to sum from 1 to infinity from minus 1 power n over n times x power n minus 1. Okay. In the end, we get minus 1 power n times x power n minus 1. Okay, because in the way I got f prime, it doesn't help me too much. I will put 1 minus 1 in front. And if I put minus 1 in front of the series, now minus 1 inside the series, at which power will appear? N?
N minus 1.
Exactly. Why I'm doing this? Because I want to have that x and minus 1 have the same power. That's the reason why I'm doing this. Okay, so this now can be written as minus 1. Minus 1 times x, that's minus x, power n minus 1. Now, if I want, I can denote n minus 1 by something, let's say by k. So we get the sum now. I will take it in function of k, but k will start from how much?
0.
0.
Till infinity. Okay, so I have minus x power k. And who can help me here to tell me how much is the sum of that of the last series? Because what we got, it should be well known for everybody.
Minus 1 over 1 plus k. 1 plus
X.
x.
Exactly. Good, thank you. Very well. Because, of course, for the modulo of x less than 1, but what we applied, remember the geometric series, 1 over a, we can expand it as the sum from 0 to infinity from a power n when the modulo of a is less than 1. Yeah, so I applied this formula. In our case, a it's minus x, so we got the fact that f prime it's minus 1 over x. Good. But if f prime is minus 1 over 1 plus x, then how much? Okay, how we determine f in this situation? We?
Integrate.
Exactly. So it will be minus integral from 0 to x from 1 over, I can't put the x, I will put, let's say, t in this case. So we get minus logarithm of 1 plus t with t from 0 to x, and immediately we obtain the logarithm, minus, of course, the logarithm of 1 plus x. That's f. But remember that we don't need f. We need x. We need s of f. Let's lift a little bit the page. But don't worry, if you didn't manage to write till now, I will come back to this point in a few seconds.
Actually, I have a bit of a question.
Yeah.
If you go back to s of x over x,
Yeah.
will we write back will we write the sum by x?
Yeah.
Shouldn't we start from 0 since it's a division term by term, and so you instead of never mind. Now that I said it aloud, I get it. Never mind.
It's okay?
Yeah, it's okay, it's okay.
Good. But you remind us of the fact that as I divided at some point by x. So now, because you remind us now that, let's come to that point. So s of x over x, it was how much if you look, but I unfortunately can't manage to lift the page such that, okay, I think now it's okay. So look here, just a second to take a color. So look here. We have the fact that S of x over x, it's exactly f of x. Yeah? You saw from that equality.
Yes.
Is it now? When we have one more step to perform and we finished. From here, it means that S it's x times f, but f we have it, so my series, it has the sum minus x times the logarithm of 1 plus x, and we finished finally. Okay, and this is it. Questions? So at this exercise, usually at the seminar we worked with examples where we had to derive or to integrate directly, yeah? That was the idea. But here, this exercise was a little bit tricky, yeah? Because I couldn't derive the series I had. I had to do something first. I had to divide by x and then to derive it. Yeah, so it was a little trick to use. But after that, the things were simple. Okay. Questions? Let's have one more exercise where I will ask you to determine the domain, only the domain of convergence for the following series. Yeah, because as I said, they want a revision of the power series. We continue with the revision of the power series and those expansions. Okay, just a second because I have to search. I have a list with some exercises. So determine the domain of convergence. The domain of convergence. For the following. Power series. Now, we'll start with something, let's say, easy. Yeah. My aim is to solve exercises for all the levels. So that's why I prefer to start with something easy, then I will increase a little the level. So first, let's take, for instance, the series of general term, I don't know, let's say 5 power n over n squared plus 1 times x power n. All right, another one. Let's take, what to take? Okay, I will take this one. The series of general term n over 2 power n minus 1 times 3 power n times x power n. Another one. Now, I will take the series of general term. Let's take for this situation n power the logarithm of n times x power n. And the last one, just a second. The the last one we take, it will be the series of general term square root from the logarithm of n squared plus 1 times I will take x plus 2 power n. Yeah. So here we have problems for all levels. Now let's start the work. As we learned at school, we discussed about those things and last week. Now, one more time, we'll make a revision at this part to be sure that everybody understood them. After this part will be finished, then we go further and continue with something else. Okay, good. Let's start. So, solution. So, the first exercise, actually, what I did in the previous exercise to determine R, the radius of convergence, and so on, that's what I will do here. So I start to compute R, the domain of, the radius of convergence. I will use the formula with AN, with the model, of course, of AN over AN plus 1, where I didn't write, but I will put it here. AN, in my case, that's 5 power n over n squared plus 1. Okay. Quickly, let's come and replace. But look at AN. It has only positive terms. That's why I won't put the module anymore. Just put how much here. It's 5 power n over n squared plus 1 times the reverse of AN plus 1. It will be n plus 1 power 2 plus 1 everything over 5 power n plus 1. Okay, I will simplify by 5 power n. Yeah, it will remain only 5 here. And everything here equals to limit, and n goes to infinity from, let's compute a little bit, and at the numerator it will be n squared plus 2n plus 2 everything over n squared times 5. I will put 5 in front of n squared plus 1. Now, everything becomes, let's continue computations over here. But I think I can write directly. How much is that limit? Who can tell me?
1 over 5.
Exactly. 1 over 5. So quickly I will write the fact that this power series is convergent, as you know already the story, what it comes, it's convergent for x in the interval. Here it will be minus 1 over 5 and 1 over 5, and divergent for the interval. Yeah, here what I think it's actually an application of the Abel's theorem you learned at the course. Okay. Divergent for x in minus infinity minus 1 over 5, reunion by 1 plus 5, 1 over 5 plus infinity. Okay, here it's a parenthesis, but I don't know why it appears like this. Now, as we are already used, we start to study on plus and minus 1/5. So when x is 1/5, I get the series of general term 5 power n over n squared plus 1 times. When x is 1/5, actually we get 1/5 power n. So we simplify and we get 1/n squared plus 1. Now, this series, it will have the same nature by using the limit comparison test because it's a series having positive terms. It will have the same nature with which series?
1/n squared.
1/n squared, good. Okay, which I hope we all know that this one is convergent. Right, let's move forward. Good. For the other point, in minus 1/5, let's see what we get here. This one. I have also 5 power n over n squared plus 1 times minus 1/5 power n. This can be written. It's obviously that I will simplify by 5 power n, and we get minus 1 power n over n squared plus 1. Okay, here it's an alternating series. What will happen with the nature of this one?
It will be
Convergent.
convergent.
Exactly, is convergent by using the Leibniz test, of course. Let's put here between a parentheses the Leibniz test. Okay. The Leibniz test. So the domain of convergence for the first series, it will be the closed interval both sides minus 1/5 and 1/5. And we finished. This exercise asks us only the domain of convergence. Okay, good. Let's continue with exercise B. But what we have at exercise B, if you wrote, please help me because I don't want to lift the page. Maybe there are some colleagues, they didn't write. So can you help me what we had?
N over 2 at power n minus 1.
Yeah.
Multiply by
I think it
x
was
to power n.
It was
yes,
times
to power
3. Yeah. But here, surely it was n, only n.
Yes.
Oh, okay, thank you. Good, thank you for your help. All right, I didn't want to leave the page because maybe some students, they didn't manage to write, and it will be disturbing for them to leave the page and then come back. Good. Here, for this series, okay. An, who it is? It will be n over 2 power n minus 1 times 3 power n. I wrote it because I want to have it in front of our eyes when we start to compute the radius of convergence. So we have the limit when n goes to infinity from the modulo of an over an plus 1. So like we did in the previous exercise, just we start to replace because an it's all the time positive, we don't put the module anymore. So we get n over 2 power n minus 1 times 3 power n, okay, times the reverse of n plus 1, which means 2 power n times 3 power n plus 1, everything over n plus 1. Okay, we will make all the simplifications. Here is 2, here it's 3. So we get limit of when n goes to infinity from 3n over n plus 1. Okay, how much?
not 6n?
And I missed, yeah, thank you. I missed something. So it's 6n, isn't it? Yeah, we missed.
Yeah.
Yeah, good. So it's 6. And so from here, the limit will be how much?
6.
6.
Obviously, it's 6. Good. So the series from this exercise, you know, that's convergent for minus 6, 6, and divergent for minus infinity, minus 6, reunion with 6 plus infinity. So I will write fastly this. Okay, 2 power n minus 1 times 3 power n times x power n. Okay, it's convergent for x minus, in minus 6, 6, and divergent for x in minus infinity minus 6, reunion with 6 plus infinity. Okay, now I start to study for 6 and minus 6. So let's do it. If you want, you may work in advance. It's not necessary to wait for me. These are simple computations, so maybe you may work in advance and then check if you got the same answer. Okay. So let's do it for x and x equals when x equals to 6 and then when x equals to minus 6. I will take, let's say, x equals to 6 and see what we get. That will be n over 2 power n minus 1 times 3 power n times 6 power n. Good. Okay, of course I can simplify by 3 power n, also by 2 power n minus 1, but when I do that, how much I will get to the numerator?
2n.
Exactly, 2n. Okay, the 2 doesn't mean anything, but so I got this series of general term to n. What about this one? It will be how?
Divergent.
Divergent.
Exactly. And if you wonder why, if there is someone who wonders why this one is divergent, well, the reason why it's simple, because the general term has the limit plus infinity, so it's divergent. And we put between a parenthesis the necessary test, yeah, to be clear what we apply. The necessary, here it's y test. Good. Well, quickly to the other point, we'll check what we get. So for x minus 6, it will be n over 2 power n minus 1 times 3 power n times minus 6 power n. Okay, but when I will make all the simplifications, I get -1 power n, and 2 also. Yeah, but even this series, what will happen with it?
It's convergent. Divergent, sorry.
Exactly. What happens here with the limit of the general term, if you look a little bit?
Doesn't exist.
Exactly, because the limit of the general term doesn't exist, is divergent too. It's divergent. Also, the necessary test I put here. The necessary test. Okay. I repeat because the limit of the general term doesn't exist. So if you remember the necessary test, it means that this series is divergent. So for this exercise, the domain is the, so it remains actually the opened both sides interval -6, 6, and we finished with this one. Okay, questions? If you have a question, I don't mind. Every time you feel the need to ask something, it's okay. You can interrupt me and ask me, because it's better to clear every question you have.
I have a question.
Please.
So, you get like for 6 and -6 is divergent, yes?
Mm-hmm.
So, in this interval, the series is absolute convergent only, no?
Yeah, it's on -6, 6, it's absolutely convergent, which means that's also convergent.
Yes.
The request of the exercise, it wasn't to determine the domain, the domain where the series is absolutely convergent. It asks us where it's convergent, but you know, from the Abel's theorem, on -6, 6, it's absolutely convergent. Okay, but I know something else. If it's absolutely convergent, well, it means that's also convergent. Yeah.
Yes.
Mm-hmm. Yeah, but the exercise doesn't ask us domain where it's absolutely convergent. Only the convergence.
I know, but it was a
Mhm.
question.
Mm-hmm. Mm-hmm. Yeah. Okay. Did I manage to answer you?
Yes, of course. Thank you.
Good. Mm-hmm. Okay. Next, maybe if you want to help me one more time with the following series, because I don't want to leave the page. Yeah, it will be annoying for you to do that. Just help me, because I don't remember exactly what I wrote, which exercise. I have a long list with exercises and I don't remember which one I chose for exercise from point C.
N to power logarithm n
Yeah,
multiply by x to power n.
yeah. But then it was from how much here?
1.
Please modify a little. Yeah, please modify. It will be from 2. I want it to be from 2. No. Okay. Right. Let's start. What I do here, what I know to do, isn't it? To determine the radius, yeah, and then to apply the Abel's theorem. But at this exercise, the difficult part is to get the radius, because to check on the extremities, it will be easy to do that. Okay, still let's try to determine the radius. I will use the formula you are already used with it. one with the modulo of an over an plus 1. Of course, an is positive, so actually the module is not necessary to use it here. Okay, so we have n power the logarithm of n over n plus 1 times the logarithm of n plus 1. Okay. And now what to do to compute this limit? Let's see. That's the problem at this exercise. Yeah.
It is possible to denote logarithm with something.
Okay. If it's possible anything, but I don't know if it will help us. Yeah.
Maybe we can use
Yeah.
functions.
In the end, yeah, we'll use functions. Otherwise, we won't be able to compute this limit. Yeah, you see that it's infinity actually over infinity. So we can use functions. After that, we use L'Hopital and so on. But to be more easy, even when we compute we use functions. Look at something. Remember the fact that the exponential and the logarithm, they are, you know, what's the bond between them. For instance, if I have e power the logarithm of n, do you know how much is this? E power the logarithm of n. It's a simple question.
It's n.
It's n. Good. Obviously. And e power the logarithm of n plus 1. It's n plus 1, isn't it? Okay. But what will help us? Well, I will come back to my limit. And instead of n, I will put e power the logarithm. So I get limit when n goes to infinity from, instead of n, I put e power the logarithm of n. So it will become e power the logarithm of n all power the logarithm of n. As the denominator, the same idea I will use. So we have e power the logarithm of n plus 1, everything power the logarithm of n plus 1. Good. So what we get if I do that like this? It will be e power the logarithm of n, but power 2, isn't it? And at the denominator, it will be e power the, sorry, e power the logarithm of n plus 1, power 2. At least till now. Is it clear?
Yeah.
Okay. But that's something easy by using the elementary properties of powers, yeah, of operations with powers. What I got here, actually that's e power the logarithm of n power all power 2 minus the logarithm of n plus 1 all power 2. Is it correctly? Is it correct what I wrote?
Yes.
Good. Now,
And
yeah.
I'm going to get back to use the formula for a minus a square minus b square.
Yeah, but
Yeah.
look what else I will do here. The limit of e power something, what I have there. Actually, that's e power limit when n goes to infinity of this term we have at the power. Yeah, and I have to put it like this now. Do you agree with that? It's these are some properties of the limits. Yeah. So look at what I got. Look at, yeah, the limit from the beginning. Now, everything is reduced to the computations of what? To the computation of limit. I will write, let us take, we'll take below limit when n goes to infinity from the logarithm of n power 2 minus the logarithm of n plus 1 power 2. So I have now to compute this limit by using the what your colleagues said, that formula a squared minus b squared. I will use it immediately, but just a second, because I want to be sure that everybody understood. So I take here below this limit. After that, after I will get the result, what I do, I come back and all the limit, it will be e power the value of the limit we have to compute now. Is it clear what we have to do? Questions? Yeah? Okay, good. So now, yeah, I will use that limit, that formula a squared minus b squared. It will be useful here. But first, let's look at something. That limit, it's infinity minus infinity. And you know that's an undetermined case, yeah? So I have to do something to be able to compute this limit. Otherwise, I don't think we can obtain it. All right, it's the logarithm of n minus, here it's minus, yeah, the logarithm of n plus 1 all times the logarithm of n plus the logarithm of n plus 1. Yeah, I use that formula. But you know that the logarithm, it has some property. For instance, the first parenthesis, how can we write it one more time by using one property of the logarithm? It will be the logarithm of how much?
N over n plus 1.
Exactly. Good. Times. Also, I will use another formula for the second parenthesis, which is?
Logarithm of n multiplied by n plus 1.
Exactly. Okay, but what we mark now? I have what I got here. I have the logarithm of n over n plus 1. That's how much it's the value of that limit.
It's 0 or infinity.
Exactly. So another problem, it's 0 times infinity, which you know that's an undetermined case also. Yeah. But maybe instead of writing this parenthesis like the logarithm of n over n plus 1, I wanted to write it like this. To see that's also an undetermined case. It's 0 times infinity. And in high school, when you had, sorry, I don't know what happens, but the pen I use to write, it causes me problems. Okay, in high school, I said, when you had 0 times infinity, what you used to solve the problem? Because you know you can't apply L'Hopital in this situation, yeah?
We put 0 under like infinity over 0.
Yeah, so yeah, good. So probably you met this kind of situations, yeah. And there is a trick that can be done. Of course, in my exercise, I can't use L'Hopital because we have sequences, we don't have functions. But don't worry, we'll take the associated function and we'll do it. But for the moment, so the logarithm of n over n plus 1, I know that's 0. Now, because I want to solve the problem, instead of the logarithm of n times n plus 1, I can write it as 1 over the logarithm of n times n plus 1. And let's look. Is it okay? It's the same value.
Yes.
But now what I have? I have the logarithm of n or n plus 1, which has the limit 0. And 1 over the logarithm, how much it has the limit?
0.
Also 0.
So which is nicer, isn't it? But as I said, I want to leave the logarithm of n over n plus 1 because it won't help me too much when I will try to use L'Hopital. So I will come back to the fact that that term is the logarithm of n minus the logarithm of n plus 1 over 1 over that logarithm. Now, I will construct the associated function immediately. So let's take f. Let f of x. I told you the fact that the pen I'm writing with, it causes me problems. So it's the logarithm of x minus the logarithm of x plus 1, everything over 1 over the logarithm of x times x plus 1. And now I want to compute the limit when x goes to infinity of x. Okay, let's do it. So we have limit when x goes to infinity, when x goes to plus infinity from. And now I start to apply L'Hopital. I think we can use L'Hopital directly, yeah, because we saw that 0 over 0, so it's good to use L'Hopital. The derivative of the numerator, it will be 1 over x minus 1 over x plus 1. And now, can somebody help me with the derivative of all this term 1 over the logarithm of x times x plus 1? Who can help me? It's a little bit more difficult, I know. That's why I asked you. Because I want to check if you remember how to derive. You have a composite function, but it's not too difficult to do it. First of all, 1 over f. Let's remember a little bit from high school, yeah, with this occasion. 1 over f derived. In general, if f is a function, how much will be? Do you remember the formula?
Minus 1.
Minus, it was minus f prime over f squared. Do you remember now? Yeah?
Yes.
All right, so let's do it in our case. It will be 1 over f, it's the logarithm, so it will be the logarithm squared of x times x plus 1. F prime, it's the derivative of the logarithm. Yeah, the derivative of the logarithm of x times x plus 1 derived, how much it will be? It will be 1 over x times x plus 1. But I didn't finish because it's a composite function. And I have also to derive what? X times x plus 1, isn't it? Do you remember the formula for the derivation of composite function? Let's remember it. Maybe somebody forgot it and it will be helpful. Remember that it was f of g of x, yeah, times g prime. That was the formula. Of course, in our case, it's a little bit more difficult, but we have to do it. It's not impossible. So times, who can tell me what's next? I hope you didn't forget to derive.
2x plus 1.
Exactly, good, very well. Who said? Unfortunately, I haven't the screen with your names in front of my eyes. I can't see you, so that's why I asked you, because...
Maria.
Very well, Maria, yeah, good. Okay, now we have to perform some computations, unfortunately, because we still have work to do. I will continue here, let's say. So we get limit when x goes to infinity from plus infinity here, yeah. I will amplify here by x plus 1, here by x, and we get 1. So at the numerator, it will be 1 over x over, so 1 over x times x plus 1 all over minus 1 over the logarithm power 2 of x times x plus 1 times 1 over x times x plus 1, which is good because what I will do immediately, I will get rid of that term, and also it is 2x plus 1. Now, this also can be written as limit when x goes to infinity from minus the logarithm of x times x plus 1, or everything over 2x plus 1. Okay. And if you look, that's infinity over infinity, isn't it? But you have the logarithm, and at the denominator, you have a polynomial, actually, if you look, of degree 1, of first degree. So who can tell me how much is this limit? Well, how much? Well, think in the following way. You have, you know from high school, the fact that the polynomial function, it's quicker when it goes to infinity. So even if I have the logarithm squared, how much do you think all this will be?
It's 0.
Yeah, if you aren't sure, well, you may use the L'Hopital theorem one more time and get it, but it's easy to check, that's 0. Yeah, but as I said, you see that's infinity over infinity, so nobody disturb us to check if indeed it's 0. But I think what will happen, we have logarithm squared, so it will be, when you derive above, it will be 2 times the logarithm of x. Yeah, maybe to be sure, yeah, maybe someone is not sure or he didn't understand, so let's prove indeed it's 0. Yeah, for those who didn't understand how I got that value. So I apply L'Hopital one more time, minus it was written in front. I start to derive, but also a composite function, so we have to be careful. It will be 2 the logarithm of all that times logarithm derived, it's 1 over x times x plus 1 times what? 2x plus 1. Minus 2, I can write it in front. I have limit when x goes to infinity. And I will group a little bit the term. For instance, 2x plus 1. I can put it, for instance, over x plus 1 times, what's missing? It's missing the logarithm of x times x plus 1 over x, yeah? But the first one from here, it has the limit how much when x goes to infinity? It's
2.
It's 2, good. So it goes to 2. But the second one, what happens?
It will be 0.
Logarithm, exactly. Yeah, because I repeat, the logarithm is slower when it goes to, so I think in this case it's more clear why indeed all this is 0. Okay, so it was a lot of work. Now I'm not sure if everybody managed to write, because I will need to leave the page. Is there somebody who didn't manage to write? Okay, if nobody says anything, then I feel free to leave the page. So look what we worked. Only for the limit of the logarithm of n power 2 minus the logarithm of n plus 1 power 2. We proved that that limit is 0. So now I have e power 0, which is 1. Yeah. But what we obtained? I obtained the radius of the power series. So finally the radius is 1. So I can continue. So r equals to 1. It means that the power series n power the logarithm of n, it will be convergent for x in the interval -1, 1, and divergent for x in minus infinity -1, reunion with the interval 1 plus infinity. Now, as we are already used, we have to check. It will be for x when x equals to 1, and then when x equals to -1. But when x equals to 1, at least this part is easy. What we get? We get n power the logarithm of n, and just by looking at the limit of the general term, what can we say about the nature of this series? Is okay, how much is the limit of when n goes to infinity of n power the logarithm of n? It's
Infinity.
Sorry, I didn't hear.
Infinity.
Yeah, good. It's plus infinity. Well, then it means that the series is divergent from the necessary test. Yeah, the necessary test. Okay. Let's check. Let's check for -1. For -1, I get -1 power n times n power the logarithm of n. Okay, now what happens with the limit of the general term. Limit when n goes to infinity.
The limit doesn't exist.
Exactly, the limit doesn't exist. Yeah, the limit doesn't exist. Doesn't exist. So also the series is divergent. So in this case, the domain of convergence, it will be the interval -1, 1, but opened, yeah, opened. Here it's visible. I hope that's opened. To be the opened interval -1, 1. And that's it. Okay. Questions?
I have a question.
Please.
When we get to put e in the limit at the beginning,
Yeah.
can't we
Yeah,
use,
I will, let me lift a little to have in front. All right, here, I suppose.
yes, after we
Mhm.
first put it, can we put like
Here and here.
can we already say it's 1 because the limit it will be e to the power oh no, wait, no, I
No.
made a mistake. I just saw. Sorry.
No, it does. You want to say probably it has the same degree or something.
Yes, I want to say it has a
But
sentence, but it doesn't work.
no.
I put a wrong parenthesis on the line I was
Ah,
looking at.
all right.
That's
Yeah,
why we did.
yeah, it was good. Look, we lost a lot of time with this exercise. It's long. Yeah, but I wanted you to show you because I told you, I think, from the seminar that those meetings, these meetings will work for all levels. Yeah, one exercise will be trivial, another one we will increase a little the level and so on. Yeah, because I think it's the best way to work. Yeah, I want to show you in some exercises which are more interesting than what we usually work at the seminar. At the seminar, we don't have too much time to work everything, but at least we have those meetings and we afford the work and something else. Okay, exercise D, I will leave you as a homework. Yeah, take it. So exercise D, we leave it as homework. Yeah, try to. It's easy. It's not what we had at exercise C, don't worry. It's not so difficult. Yeah, it's easier. It's much more easy than what we worked. And now let's continue with expansions in power series. And after that, some approximations. So the
Sorry,
yeah.
I wanted to ask you because I
Yeah.
didn't get the trick with E. How was possible to introduce it?
Yeah. Just a second to come back to that part. Here, when I wrote, what happened? When I wrote e power the logarithm of n at that part.
Yes.
Okay, I see that the screen doesn't leave us, but don't worry. It won't be a problem for us because we can write one more time here. Why it's possible? Because in general, the exponential and so if I denote by f the exponential and by g the logarithm function, you know that they have something in common. F, so their composition, it's the identical function. Yeah, identical function. Or they are reverse one to another. That's why all the time e power the logarithm of x Well, but here not on R. Actually, that's 0 plus infinity. What we have. The identical function, do you know what it means? It means that 1 of x, it will be exactly, that's the identical function, yeah? So all the time you have this formula for any x from 0 plus infinity. Did you know this equality?
Oh, yes, I remember now.
That's it, because they are reverse one to another, yeah?
Yeah.
So that's why we have this equality. Okay, it's okay?
Yes, thank you.
You're welcome. Okay, let's go and talk about expansions in power series and then some approximation. Yeah, like the exercise, the classic exercise we solved at the seminar at the course 2. Yeah, I remember that you had to approximate an integral. That's what we'll do all together. But first, let's do something else. So expansions in power series. I wanted to show you some interesting, an exercise very interesting, but because it's already late and there is no time to work everything, and this type of exercise, it won't be included to the exam. I think it will be better to leave it for next week when you won't have the partial, and that's we may work in class. But for the moment, I will focus on the exercise you will have at the exam. So expansions in power series. Okay. But let's take the following type of exercise, for instance. At the first point, I would want to expand. So expand in power series the function f of x be the logarithm of 1 plus x. At the second point, I will want to compute with an error epsilon less than 10 power minus 3 the integral and the integral that's integral from 0 to 1 over 2, but just a second because I want to check in a book I have. I'm not sure about the interval. Let's check it a little. Just a second, you have to wait for me. Okay, it's okay. So it's integral from 0 to 1 over 2 from the logarithm of 1 plus x over x dx. Okay, let's do it. So the first point, solution. What can we do to expand in power series the logarithm? What ideas do you have? Let's see.
First of all, we have to derive it, the logarithm.
Good, very well. Yeah. Why we derive? Because among all those elementary expansions in power series, you don't find the logarithm. So we have to do something, yeah? So one idea, it's a classic idea actually. I think I showed you for the arcsinus, for the arctangent, for the logarithm. I told you at the seminar what's the idea. So let's take. It will be 1 over 1 plus x. But 1 over 1 plus x, I know how to expand it in power series. It will be sum from 0 to infinity from -1 power n times x power n. But if you want, if it's not clear for somebody why, how I think it will be 1 over 1 minus x, yeah? And also I will remind you the fact, yeah? So I write 1 over 1 plus x like I told you. And also I will remind you the formula 1 over 1 minus a, that's sum from 0 to infinity from a power n, of course, when the module is less than 1. Yeah, so we use this formula. I prefer to write it because I wanted to be sure that everybody understands. Is it clear till now?
Yes.
Good. Now, okay, so I have f prime. Of course, I don't need f prime. So now what do we do to get f? We
integrate.
Yeah, we integrate. So integral from 0 to x from sum when n is 0 to infinity of from -1 it's here power n times x power n. But here I think I told you the fact that you won't put, because I put integral from 0 to x. I won't put also x, I put, I don't know, t, and here I have to put dt. Now, I will integrate term by term. It means that the integral of the sum, it will be the sum of the integral. Also, -1 power n, I can write it in front. T power n integrated, how much we get?
T power n plus 1 upper n plus 1.
Exactly. Over n plus 1. Computed from 0 to x, and everything transforms in sum from 0 to infinity from -1 power n over n plus 1 times x power n plus 1. Yeah, n plus 1 here. Good. Okay, so that's the expansion. Of course, I have to put the fact that the modulo of x must be less than 1 because the expansion in power series, it works only when the modulo of x is less than 1. So I will write one more time what I got. It means that the logarithm of 1 plus x can be written as an expansion in power series of the form -1 power n over n plus 1 times x power n plus 1 for any x in the interval -1, 1. And in this way, I finished with the first point. Okay, let's see. Is it clear till now? Questions?
Now it's clear.
Thank you. Okay. Good. So till now I have the logarithm. Let's move to exercise B, to the point B. Now, as we already did at the seminar, now, because from the first point, I have the expansions of the expansion of the logarithm at exercise B. What I do, I take the integral. Okay, first I will write it one more time. Now what I do? I expand in power series the function under the integral. But for the logarithm, I already have from the previous point its expansion. So we get integral from 0 to 1 over 2 from, and now I will copy sum from 0 to plus infinity for minus 1 power n over n plus 1 times x power n plus 1 everything over x. Yeah, so at the numerator I just wrote the expansion in power series of the logarithm. So everything over x dx. Now, because x, it doesn't depend on n, it can be put it under the sum. So actually we get integral from 0 to 1 over 2, sum from 0 to infinity, 0 to infinity, from minus 1 power n over n plus 1, but how much it will be next? X power? Well, I have x power n plus 1 over x, but that's x power n.
And
Yeah, because we simplified by x. Okay, but I didn't finish. We continue with the computations. What I did. Okay. Okay. No, it's the moment to do what? I have the integral of the sum. Now, by applying integration term by term, we already mentioned that at the previous point. That's actually, so the integral of the sum, by applying the theorem of integration term by term, I get the sum of the integral, but minus 1 power n over n plus 1, that's a constant. So here when I apply the integral, that's integral from 0 to x from t power n dt. Yeah. Or if I write one more time by integrating, of course, that can be written as from 0 to infinity from minus 1 power n. But sorry, I made a mistake, isn't it? It's not 0x, it's how much? 1 over 2, isn't it? And there is no need to put t in this case, just, okay, it wasn't a mistake to leave a t, but there is no reason to change here. The integral is from 0 to 1 over 2, yeah, okay. So it's minus 1 power n over n plus 1 times, I integrate its x power n plus 1 over n plus 1, compute it from 0 to 1 over 2. And what we get finally, it will be an alternating series, yeah, of general term minus 1 power n. And here, n plus 1, if you see, it appears 2 times, so I think I will put n plus 1 power 2, but also at the denominator, it appears n2 power n plus 1. So, my integral, in the end, I prove that's actually an alternating series where an, it's 1 over n plus 1 power 2 times 2 power n plus 1. No.
And because it's an alternating series, we can approximate it, right? If it wasn't, it would be harder to approximate.
Good. So now I can apply the algorithm of approximation you learn at the course to approximate an alternating series. Good. So remember what I told you at the seminar. The idea is to get the least natural n0, let's say, such that an0 plus 1 is less than the error. So what I do, I start 4 and 0. I don't take a0, I take a1, if you remember. a1, how much it is in my case? Well, I replace here. Yeah, I go here, and when n is 1, it will be 1 over 2 power 2, that's 4, times also 2 power 2, that's 4, so actually it's 1 over 16. But what do you think? 1 over 16, it's less than 10 power minus 3? What do you think? Huh?
No, it's not.
Of course, it's false. Yeah. Okay, we have to move to another one. Okay, the next one. Yeah, I do that till I will get the inequality, till the inequality holds. So when n is 1, I have to check for a2. It's 1 over 3 power 2, that's 9. 2 power 3. Unfortunately, not even in this situation, I don't think we get something. It will be 1 over 72, which, what you can say, true or false?
It's false.
Yeah, unfortunately, it's false. False. Next, 4 and 2. I have to check for a3. Okay, I have 1 over 4 power 2, which is 16, times 2 power 4. Okay, 1 over 16 power 2. Unfortunately, that's also false, isn't it?
Yes, it is.
Yes.
Yeah. At some point, we have to know that the algorithm, it's finite. So at some point it will stop. Don't worry. We won't do this an infinity of times. Yeah, at least. But at which point, I don't know. Just we have to make the computations and see what happens. Okay, 1 over, so a4, it will be 5 power 2, that's 25. 25 and 2 power 5, how much it is? 32, I think. I think I will need some help with the computations. Please compute 25 times 32 to see what we have.
800.
Exactly how much?
800.
Okay,
Simply.
thank you. Good. Unfortunately, it's also false, and we have to continue. Okay, but I think what we see is that from step to step, we are approaching to 1000, isn't it? So
Yes.
probably you won't have too many steps to do till we will get the final answer. Okay, I have 1 over 6 power 2, that's 36. 2 power 6, that's 64. Okay, some help, please.
2000 and
How much?
2000 and
Yeah,
204.
200.
333. Sorry, 304.
304. Thank you. That's perfect, isn't it?
Yes.
Finally, that's less than 1 over 1000. Good. So it's true. Okay. So what I said, we put 4, in this case, b and 0. So the alternating series will be approximated by S4. Okay, I have no space over there to continue, but I'll write one more time the integral. So the integral 0 from 0 to 1 over 2. From what we had, logarithm of 1 plus x over x, I said that will be approximated by S4. Now, what I do? I start and compute S4. Remember that S4, it's the sum, is the sequence of partial sums. So it will be, I will go to the alternating series. Yeah. And by having it in front of our eyes, just a second. Okay, it was a small problem with the internet. Now, can you hear me?
Yes.
Good,
Yes.
thank you. Sorry for the disturb. It happens. All right, so I will come here to the alternating series. Let's take a color, let's say a red one. And now I start. S4 is the sum of is the sequence of partial sums. So I start the first term plus the second and so on. But yeah, I said plus, but it's an alternating series. So sometimes it will be plus, sometimes it will be minus. So we have to be careful how we write it. Okay, but the first term, when n is 0, we see that it will be minus 1 power 0. That's 1 over 1 times 2 power 1. So the first term, it's 1 over 2. Next. So 1 over 2 minus. It will be minus because n it's 1. I don't have in front of my eyes, but you have the alternating series. And how much we have? It will be minus a1, which we already computed. It's 1 over 16 plus a2. It's 1 over 72 minus a3, which is 1 over 16 power 2. Well, I didn't compute it here. Plus a4, and here I will stop. Yeah, because that's S4. Of course, now we should perform all those computations. Yeah, we won't do that. And I decided if you will bring the exercise till now, I will leave it the maximum, yeah, the total points, because I think everybody knows how to work with fractions, and if you get something like this, it's more than enough. Yeah. Okay. Questions? Okay, that's all for today.
So, actually, why was it up to n equals 3, not n equals 4 for I mean...
We take n equals 4 because n equals 4 is the first natural number such that a and 0 plus 1, it's less than the error. When n
Yeah,
is 3, you see that it's false. Yeah.
yeah.
So we can't take it. That's the problem with 3.
No,
So-
no, but why don't we subtract for the fifth term as well?
We don't take the fifth term because so the idea was to find n0. I will put like this, such that n0 plus 1 be less than, so n0 plus 1, yeah, be less than the error. In our exercise, it's 10 power minus 3, but that's not mandatory, yeah? So that's why we don't take a5.
I get it. I understand.
Mm-hmm,
Thank you.
You're welcome. Okay. Good. So that's it for today. I hope you already know which group, where to go for the partial exam. It's important, yeah. So with the exception of the group, well, I'm talking about my groups. Yeah, you know who has with me and who has with my colleague. But the groups, actually the group 1212A, it will have the partial exam on a Thursday at the course. Also the group, okay, it doesn't matter, this group doesn't have with me the seminar, but don't forget, if among the students that joined today, you are from 1211 B, then also you have other course, and the groups 1211 IoT, 1212B, 1211A. You know that we have on Friday at the seminar, yeah? And you know the rooms. I hope that's clear for everybody.
Yes.
Okay. Antonio, please, you raised the hand.
Yes, you told us at the first seminar that you had some exercises solved. Do you think it's possible to send us some of them until the partial to have a look on them?
Yeah, but those exercises was for sequences. You don't need for sequences. Yeah, those things, they are for the students that didn't study convergence sequences. I don't have for what we did together. Yeah, and I know that I promised for the students that they didn't study in high school convergence sequences. Sorry, I didn't upload it. One of the reasons was that, well, it was a technical problem. In the first weeks, I didn't have access to the Moodle platform, so that's why actually I didn't manage to upload anything. Emmanuel. Yeah.
Will you be making and also correcting the subjects for the partial, or will
Okay,
the
that's
course teacher do it?
I don't just a second, a little bit